Hello fellow problem solvers. So they're already doing a problem from the 2015 IMO shortlist problem number G1. And this is the original intended problem number 4 at the IMO. The reason why I wasn't at the IMO was because the problems from day 2 accidentally got out. I talked about that in my IMO shortlist 2015 problem number A1 video. So if you want to try this geometry problem out, I invite you to try it out for a minimum of 15-20 minutes ideally, 30 minutes to an hour and a half, though not more really. Actually, if you've not done geometry and if you want to go to the IMO, try this for ideally until you solve it, but at most 4.5 hours, because you want to test yourself that you can actually solve the first problem if it's a geometry at the IMO. So now without further ado, let's begin. Though actually, before I do that, if you just want to go along with us, draw a diagram, put your first ideas out on paper for the next 10 to 15 minutes, okay? So now let's begin. We have ABC, acute triangle with orthocenter H. So the first diagram that we draw, let it be something that's, not that great, just so like we see what's happening in the picture. So we have ABC, and we have orthocenter, boom, boom, H. What else do we need? So let G be the point such that the quadrilateral ABGH, so AB, and then we have GH, so this needs to be parallel, and this needs to be perpendicular to this, so that ABGH is a parallelogram. Okay, so this is a parallelogram. And then let I be a point. So actually, before we go on with I, can we figure anything out about this point H, this point G, actually, which is new? So that's sort of like solving the problem a step at a time. You want to see like, okay, what does this give me? This thing that I have right now, it's a parallelogram, like what are all the things I have? And after I figured out these are all the things I have, then I move to the next point. So let's see. We have this angle right here is equal to this one, which is 90 minus beta. Okay, so this is 90 minus beta. Where else do we get 90 minus beta? That's a question to ask yourself in these problems. I have a 90 minus beta. Where else do I have it? And the answer is, take a minute or two to pause, figure that out. Where do you have that? Well, you have a 90 minus beta here, and you have a 90 minus beta here. So you have two things. You have something that you know about G now, that it's on the circumcircle around BHC, which means that the angle GHC is 90. And that's another way to define G now. This being a parallelogram, it's okay, but it's not the best way for us to define this point. This is potentially nicer, And the way I go about this is, if I find a different definition of a point that was given to me in the problem, probably if I needed to use that this was a parallelogram, they would have said G is a point set on the circumcircle around BHC such that CG is the diameter. Like usually that's sort of a rule of thumb between how people design problems. That's how I design problems in geometry. I want to make them harder. Just like, it's a bit artificial like that, but it's done. So now let's go to the next point. This is solving at it step by step. Now I invite you for the next point to pause for the next 10 to 15 minutes, 25 to 35 if you haven't done geometry a lot, and try to push the problem further. Here's what we get on the next point. Let I be a point such that G on GH, such that AC bisects which one? HI. So it's a point here such that this is equal to this. Okay, how are we going to use that? Well, we have this point of bisection. Let's call it something. It's not actually everything we have. We have GH and we have a point on the line AC intersects CGI, again at J. Okay, so that other intersection we're going to have, but let's actually figure out, what do we have for I first? So I invite you here, if you haven't figured out anything for I invite you to pause for 10 minutes, try to figure it out. And the first thing for me here is, I know now this is 90, that's an extra condition, that's very nice. And now what do I have? I have this is equal to this. Well, let me call this point something, because it's a midpoint of a sort. I'll call this point M. And I'll call this one B1, this one A1. Why do I call them? Why did I just like name these points? Why did I introduce new points? For me, it's like I see something and I want to see if I can use it somehow. And I saw it like this is 90, this is 90. And for me, actually, why I introduced this point right here, B1, is because I know that MHC is a right triangle. And I have this as a right triangle as well. So I have MH squared. I have a similarity from this is similar to this, or MH is tangent to the circumcircle around B1H1C. This is a common pattern for me in geometry because I saw it a lot. If you have a right triangle and a height, then this times this is this squared. Same on the other side, and this times this is this squared. Right? It's good to have these similarities in the back of your mind. If you don't, mind you, what we're doing here is we're just like going at the problem forwards, 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 forwards. You can also try to stop and solve the problem from backwards and see, okay, I need to have this or I need to have that. And then from there, figure out what it is you do have. So we have this is going to be, so we have MH squared is equal to MB1 times MC. Why do I write it like this? Because now I can use the fact that MH squared and MI are equal. And I immediately get something for I, which I didn't have before. And I get MI squared is MB1 times MC, which gives me what? It gives me angles here. It gives me that this angle is equal to this angle right here. Because of, you can say side angle side similarity between this one and this triangle, right? MIB and MIB and MCI. So that's where we have, that's how we're using this fact. And mind you, we could even here, if you're feeling a bit overwhelmed, it's good to pause, take a deep breath, and try to work out these things on your own. And try to see if you get them, is something not particularly super clear, pause, and then do the problem again. Then do these things step by step. And if you do feel comfortable, then, well, you're still gonna pause now because figure out stuff about this last point, the intersection of the circumcircle of the triangle GCI and AC. IJ somewhere there. And you need to prove that then IJ is equal to AH, which is what we came here to do, it seems. So here's where you should pause another 10, 15 minutes, push it further, see what you get. And let's see what we get. We also, wait a sec, so we're gonna have this circumcircle. Well, if we're gonna have that, what are these angles? We have this angle, let's call it X. Actually, we have what X is. X is equal to this, and this angle is 90 minus alpha, because this is 90. So we get this angle here is 90 minus alpha, which is equal to this one. So this is 90 minus alpha plus gamma plus whatever this is. But we have this angle here is also, this is 90 minus alpha, and so is this angle right here. Okay, now that we have that angle is 90 minus alpha, what do we have here? We have 90 minus alpha. This angle is currently unknown to us. Let's call this X and X. And now CGI. CGI. Beautiful circle. So CGI intersects AC at a point J. Prove that IJ is AH. Okay, so what do we know? We know AH is BG. You prove that this is equal to BG. BGs. So, wow, what are we ever going to do here? I have no clue what's happening now. So let's actually take it step by step. This is 90 minus gamma, because this is also 90 minus gamma. And a 90, so many 90-degree angles. G, what do we have for G? What do we have for G? How do I even, what even is this point J? Well, we have this angle is X. That tells us, oh, maybe there's some trigonometry, but this is a first problem at the IMO, or G1. It must have some synthetic solution. There must be something that we are missing. And now the question is, what is that? And is that it? Well, I don't know. I don't know what that is right now. So what do we do? We need to calculate, let's see, what do we have? We have IC, we have the angle here is 90 minus gamma. So this angle right here is also 90 minus gamma because it's equal to this angle. Okay, 90 minus gamma, here we have 90 minus alpha plus gamma, and then whatever x is. The problem here is like, I have no clue if anything holds true for this angle x. Maybe we'll get that later. Maybe we'll get like, it needs to be something. So we have 90 minus gamma here. Do we have 90 minus gamma anywhere else? This angle here is 90 minus alpha. Though seeing it's very important layout, I wanted to double check that it's 90 minus alpha, and it is because this is 180 minus alpha. And now what do we do? Well, I'm going to need some time to think, so you're going to need some time to think too. Pause for the next 20 minutes and think about like, how am I going to now prove that IJ is AH? Like, what? Pause now. And here's the next step. So, what are we going to do here? Well, there are two sort of approaches. One is the approach I just took, which was just, let me see if, and I changed the picture up a bit. I added this line, I calculated all the angles, and I left it like this just to show you that this is me exploring. I don't know how the problem is getting solved, and it takes time to figure that out. And now the tool I wanted to use to see like if I could solve it, what that is just trigonometry. Could I get rid of J somehow and just be left with X? That's sort of the first question. And we're going to be doing that. Secondly, the first thing I wanted to show you is actually no, we're going to do that first. So let's do the trigonometry, because the other solution, I'll just make a better diagram. Or will I? So what do I need? I need IJ. I need to calculate what IJ is equal to. How do I get IJ? Well, I have this triangle with 90 minus gamma, and it can leave me with only CI. And what will that give me? I'll get IJ by the sine theorem. Theorem of the sines here is going to be CI times what? So we're going to have IJ over X, so it's going to be CI times sine X over sine of 90 minus gamma, or cosine gamma. And now we can really just forget about J and just focus on I. Now we have this X. Can we get rid of X? Right, because AH we can get through like the sine of alpha, beta, gamma, and the sort of the side lengths of the triangle. So now we need to get rid of this X, or show that X is equal to something special. Right, so here what are we going to do? So we have CI. How do I get back to the original triangle? Well, I could be looking at this big triangle, GCI, but then I'll have either this, or I can have GC, and I'll get alpha minus X, right? I'll get a sine of alpha minus X, and I'll get a sine of 90, I'll get a cosine of gamma, that will cancel out. That's going to be nice and all, though. And then actually can I forget about I at that point? If I'm at CJ, if I'm at GC, will I be able to forget about I? That's the question is, will I be able to forget about it? I'll have alpha minus X, No, it doesn't seem, it seems tricky whether or not I'll be able to forget about this x or not. And for me, the question is, how can I now try and take CI and write it in terms of something where I'll have the sign of x next time? And for me, that is looking at it in terms of, mind you, you could also perhaps finish with looking at CG. The only question then you have to ask yourself is, how do I get this angle x? That's really the big question. Or maybe you will need to figure out some things that hold true for this, the sine of the angle x. Or is it sine of the angle x or sine of the angle alpha minus x? Actually, now that I'm thinking about it, perhaps you could do something, because this is alpha minus x, this is x, and you could have this over this and then get it to this over this. So yeah, you could even go down this route, it seems. You just then get rid of x, and then you're back to CG, and really, yeah, just CG. CG, and then you can get CG through this triangle, and then you have HC, and you're done. But the way I was doing it was saying, okay, looking at this triangle, I'll get that CI is going to be equal to what? I'll get CI, I want to get it to IM. It's going to be IM times, what do I have? I have what's over IM is x, so I'll have sine of x, and then these will cancel out. And on the CI, I'll have this angle, which is sine of alpha. So I'll get that IJ, actually it's not, I get that IJ is then equal to IM times sine of alpha times sine of x over sine of x times cosine gamma, which is equal to Im times sine of alpha over the cosine of gamma. Now Im is the same as mh. This is mh times the sine of alpha over the cosine of alpha. The cosine of gamma, my mistake. And now I have Im, I have this triangle here, I have all the angles, this is 90 minus gamma, this here is equal to 90 minus beta, this angle is alpha, and now I have mh over cosine gamma, so that's cosine gamma is this, is going to equal sine of alpha times sine of alpha over, it's going to equal AH over sine of alpha, i.e. we have this is true. And now this gives us AH is equal to this, which is equal to this, which is equal to this, and so AH is equal to IJ. And that's a way to solve it. Now a different way would be to say, okay, I have this point J. How can I use it? How can I use the fact that it's on the circumcircle, and how can I get my lengths? And I'm working with length at the same time, how can I combine those two things? And the idea is, well, I have power of point with M. And I get that MI times MG is MC times MJ. And I also can have this as MI is equal to MH times MG. And now what is MH times MG? Well, it's the power of point with respect to this circle. Right? Now, these are different types of powers of points, right? This is an internal one and this is an external one. So how can we use this internal power of point? What can we do with I and J? And the answer is we can reflect J over M and call this point that we reflected at, call it T. And then MJ times MC is equal to MC times MT, which is the power of point with respect to this circle. So we have T lies on this circle. Or in other words, GT is 90. But what do we also have? We have IJ is reflected over H, J is reflected, I is reflected over M, J is reflected over M. So that means that IJ is equal to HT. And now what we have to prove is that HD is equal to AH. And then that you have from angle chasing, or from, in fact, this is 90 minus gamma. So this angle right here is also 90 minus gamma. And then this is equal to this. And you're done. And that's a way to another way to motivate it is, we already reflected this here. Well, we want to get this closer to H. If we reflect over this point, we get I to H, we get Y to T, and we're done. And this is probably why I'd say G1, because the solution is just like reflect J over with respect to M, and then angle chase, and you're done. So these are two ways to finish the problem, and it goes to show, like in the IMO, these problems, mind you, usually have a synthetic solution. This is using power of point, or sometimes you can finish up with just trigonometry, just like bam, 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 done. And that's why it's useful to know some trigonometry. Just what you need to know is the basics of how do you get one length to another using the angles, and how to get everything closer to the elements of the triangle, the sides and the angles, the sines and the cosines of the angles. This finishes up the problem, and as always, thanks for problem solving.